All right, so today we're going to talk about a type of problem called wind and water current. And these are, here's what's sad. The likelihood of you dealing with wind and water current in your real life is very minimal. The likelihood of you dealing with money throughout your lifetime is very large. So we do need to be aware of money. And congratulations on seeing a day that happens once every 4 years. This is leap year for us. So what I need to talk about is every motion we make is not generated by our own rate. We are aided or we are hindered by a different rate. If we're on land, wind plays a factor. It may not feel perceptible, but it actually is making a factor. When we talk about wind problems, we tend to talk about big objects like a plane. Not so big objects, but still in the sky, would be a bird. Okay? And the effects of wind on planes and birds is way more than what we feel, though we've had some really gusty winds, and we can feel it when we're driving in the car with our parents, and we can feel it when we're on our bicycle. You guys should feel it if you ever ride your bike down on the boardwalk at the beach, regardless of what the day is. One way is easy and one way is hard. And some days it's worse because there's this additional higher wind than what we're used to. When you are in a boat, when you are surfing, when you are on a paddleboard, any of those things, you have one direction that's super simple and one direction that you feel like your arms are going to fall off because they're burning. That has to do with the current of the water, okay? And so the current can help us or hinder us. The wind can help us or hinder us. How many of you have been on a plane before? Okay. Have you guys noticed when you've been on that plane ride that going from here to wherever took a different amount of time than leaving there and coming back? It really doesn't take much in terms of routing. It has to do with wind. Okay? Lainey?
When I flew to Hawaii, we went an hour early because of the wind.
Yeah. And see, you got a boost with that one. That was kind of nice. Normally it's the other direction, right? So that happens all the time. All right. How many of you have ever canoed or paddleboard? Okay. Even on a lake, there's a direction that's easy and a direction that's more challenging. So what I want to do is give you some words and how we would interpret those. So the translation we're going to use for us is going to be uniform. Okay. And I am going to change words just so that you could pay attention to it. But let's talk about wind first, since it's mentioned first. And when we're talking about wind, we're going to use two variables. We're going to use P, and that stands for the object in the wind. What do you think the P actually means?
Person.
Not person.
Projector.
Nope. What did I tell you were the two main things that we talked about that deal with the wind?
Power. Push. Plane. Projectile.
Two objects. Push is not an object, it's an action. It would be a plane, okay? So anything kind of floating in the air, we just generically use P for plane. And P would be the wind speed. So this is object in wind speed. And this is wind speed. So we have two speeds going on, two rates, okay? Now, wind is usually broken into two categories. Do you guys know what the two categories are for when you have a wind? Okay, one deals with this part and one deals with the backside. You got not a tailwind, you got a tailwind and you got a headwind. Okay, so let's talk about those two definitions. Headwind. Okay, so headwind. If you put your hand on your head, push. What direction does your head go? Back. So what's happening is that the wind is pushing against you, which is taking away from your speed. So what we show is that your speed is being hindered or slowed down with a headwind. Okay? Now, a simple way of describing headwind is against the wind. There's an N. Against. Against.
Why is it N from national?
That's called a quotation mark.
Oh.
Okay? So this deals with the rate. This is all about rate. Tailwind. Put your hand on your backside and push. And like your body's being pushed forward, right? Shh. Okay, we're not what-ifing. We're trying to learn something. So your speed is being aided by the wind. So you're actually going faster. So Lainey gave us a great example that her flight to Hawaii landed an hour early because the wind pushed the plane that much faster. Okay? So again, this is rate. And again, you might refer to this as with the wind. Okay? And again, you'll see objects that are planes and objects that are birds, so on and so forth. So let's talk about things in water. So what we're going to use is these two variables. B is going to be the object speed. Actually, I'm going to erase one thing up here. I don't like this. I'm just going to call this object speed. Oops. Now, when I say object speed, what I'm saying is as if no wind existed, as if no current existed. Now, we know that's doesn't happen except for in a vacuum, and none of us live in one. So this is the only way we can solve these problems is looking for pure math. Okay, and pure math has to be based on very scientific conditions being met. Okay, so not reality. And then C is going to stand for the current speed. Okay, so the words that we use to deal with water tend to be downstream. All right, let's do upstream first. Upstream. And again, if you're going upstream, you're paddling against the current. So that means that your speed is being slowed down by the current. Okay? So we could also call this against the current. Think about every time you get into the beach and you go from the shore out, you're against the current. You're fighting to get out there. Just even walking through the water is a struggle because the current is pushing the opposite direction. And then the other word that we hear is downstream. And again, the speed of the current is actually pushing you along. Thank you. Okay. And that would be called with the current. However, have any of you ever been like on a raft, canoe, whatever, in a lake, and you didn't even paddle and you moved? That's the current just completely taking you where the current's going. And that's kind of a luxurious feeling where you just lay back and just float and go, okay? All right, so I'm going to give you, we probably have time for one problem, and these two problems are set up and solved the same way. Again, what it comes down to is language. It comes down to language. So you got to be able to read. So let's see, I'm going to give you, both of these have a little ugly in them, so I like that. Let's do a boat. It took 3 hours to row a boat to row a boat 18 kilometers against the current. The return trip with the current took 1.5 hours. Find the speed of the boat. And the speed of the current. I should say find the speed of the boat in still water, because that's that ideal situation that doesn't exist. Even on what we call glassy conditions, there's still a current. Okay? Okay, so there is some things that we need to understand what they're talking about in this problem. Number one, what do they mean by return trip? What does that mean?
How long it took to go back?
Okay, so what does that tell you about distance travel? Say again? It would be the same. Okay, now, thinking about the information they gave us, there's a formula we have used that deals with these ideas. So what are we going to base our calculations on with this wind and water current that deals with rate and time? Yeah. This is that distance formula, D equals RT, the dirt formula. And this is what we're going to use on the top of our chart for this problem, whereas with the investment problems, this is the I equals PRT, okay? How we're going to write this, however, is we're going to put the D at the end. So rate times time equals distance. And we've done that before when we were doing motion problems earlier. These are different type of motion problems. So let's set this up. So I'm going to say with current against current. And it doesn't matter which one you put on top and which one goes on the bottom. And the reason why I chose these words is because those are the words used. We have rate, we have time, we have distance. Okay, so it took 3 hours to row a boat 18 kilometers against the current. So that means 3 is the time against the current. And it told me how far it went, 18. So how do I write the rate against the current? Well, that's when we look at the earlier part of our notes. And how did we define something in water going against the current? What did we say? B minus C. Okay? So this R part comes from the beginning part of our notes. Okay? And then it says the return trip, which means 18 kilometers, took 1.5 hours. So I'm going to write it as a decimal. Or I could write it as an improper fraction. Actually, that might be easier. Let's do that. So we're going to write this as 3/2. And how did it say in the earlier part of our notes how to write going with the current in a boat? Say again? B plus C. So basically what we're going to do is create two equations. We're going to create an equation from our with the current, and remember rate times time equals distance. So we create 3/2 times the quantity B plus C equals 18. And then we're going to create an equation from our against.
So it's two different equations?
It's a system. We've got two different variables. We need two equations. So we have 3 times the quantity B minus C equals 18. Now, I'm going to let you in on a little secret. You got a choice here, but there's a better choice and there's an okay choice. The okay choice is distribute. The better choice, let's get rid of that coefficient outside the quantity. So how do I get rid of 3/2 on the left side? Multiply by the reciprocal 2/3. 3 goes into 18 6 times, and I'm left with B plus C equals 6 times 2 or 12. Okay, how do I get rid of the coefficient on the purple equation? Divide by 3. That gives me B minus C equals 18 divided by 3 is 6. Okay, what strategy am I going to use to solve this? Elimination. It is perfectly set up for elimination. When I add, I get 2B, my C's eliminate, equals 18. and then I just divide both sides by 2, and I get b equals 9. So I actually already answered half my question. So we get the boat's speed in still water is 9, and then I have to come up with a label that means rate. So it's got to have a distance label, which was kilometers, and it needs to have a time label, which was hours. Okay? Now let's figure out the currents rate. So I'm going to take this, and I'm going to plug it back into either original equation, and it really doesn't matter which one. So I'm going to take it and I'm going to plug it here. And I get 3 times the quantity, 9 minus c, equals 18. I'm going to just distribute, just because I could get rid of the 3 by dividing both sides by it. But I'm going to distribute, so 9 times 3 is 27, and then 3 times negative c is negative 3c, equals 18. I'm going to subtract 27 from both sides, and I get negative 3c equals what? Negative, is that 9? And then divide both sides by negative 3. And I get c equals 3. So then we would write the current speed, or the currents rate, is 3. Again, same label, kilometers per hour. Now, a couple things that are kind of neat about these problems is that you know you've made a mistake if you get negative answers. You know you've made a mistake if your current is higher than your object's rate, because then that means your object would not be able to ever move forward. Like if you ever watch the birds and they're flapping and they're just like this and they're not going anywhere, and they eventually give up and they turn around and boom, they just go opposite direction. Basically what's happening is that the speed that they are flapping their wings is exactly the same as the speed of the wind, and they just look like they're stuck. Okay?
Could you get a negative answer for like the wind ones? Because if you go up,
No. Never. 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 No negatives. No negatives in anything. Okay?